sorry. Which may be more or less familiar to you, depending if you've had a course on Lie groups and representations before. So one of them is the fact that any element of a Lie group, and in this particular case, we're going to take that group to be the group of Lorentz transformations, can always be written by exponentiating some linear combination of the infinitesimal generators of those transformations. Okay? So let me just remind you what they are. These are 6 4x4 matrices. And the 4x4 row and column labels I've just left implicit. So they're not written in this equation, but there should be a mu and a nu here and a mu and a nu here. Okay, but I'm just going to leave them implicit because we have too many labels. The rho and the sigma here, these are the 6 labels that just tell you which Lorentz transformation you're doing. So the reason there's 6 is because m01 is equal to minus m10. So these are antisymmetric in these objects. Okay. So these are just some fixed matrices which we wrote down yesterday. They have 1s and 0s. Okay. And these are 6 numbers which just tell us which Lorentz transformation we're doing. So they're the numbers that say we're rotating by 90 degrees or we're running at 100 miles an hour or something. So they're the specific boosts and rotations that we're doing. Okay. And what I told you was that all of the structure in the Lorentz group is to do with how these Lorentz transformations multiply together. And that's encoded in the commutation relations of these guys here. So the commutation relations are, and we worked this out in the last lecture, which follow just because we gave explicitly what these m's are. So these are the commutation relations. By the way, you might wonder, why did we pick this stupid notation where instead of putting, say, a capital A there that goes from 1 to 6, we've instead picked 2 indices, rho and nu, which each go from 0 to 3, but then insisted that they're antisymmetric, so there's 6 of them. Because obviously it gives a lot of room for confusion because these guys have other indices, which are mu and nu, which are the 4x4 indices. And the reason we've done this notation is basically so you can write this commutation relation in this nice way. Okay, so it's potentially confusing, but it actually allows the equations to be written in a very simple way. The questions? So the one thing I should just stress, all of the structure of the Lorentz group is encoded in these commutation relations. The reason for that is that the structure is to do with how these things multiply together. But remember that we have this, maybe I'll write this here. We have this Baker-Campbell-Hausdorff formula, which you've seen before, where if you have matrices and you multiply e to the a with e to the b, you don't just get e to the a plus b, but then there's extra corrections to this formula. And these corrections start with a commutator of a and b, and then all the other corrections are also of the forms of commutators of a and b with a and with b, and so on. Okay? So if you know how the a and b here commute with each other, then you know how e to the a and e to the b multiply together. So that's why the multiplication of Lorentz transformations or any Lie group is encapsulated in these commutation relations of the generators. Okay, so is this clear so far? I know there's this sort of spread of whether or not you've seen this before. So if people haven't seen this before, are there questions you want to ask? No? So the key thing you have to believe is that for any element of the group you can get by exponentiating something. You know this already for like simple groups. U1 you write as a complex number which is e to the I times something. Okay, the element of the group is the exponential of some real number in that case. That's the simplest example of this kind of thing. Any questions? Okay, so what we want to do is find other representations of the Lorentz group. So that means other matrices lambda which have the same multiplication properties as the lambdas. Okay? And the way we're going to do that is to find other matrices which aren't these fixed matrices M, but different matrices, which obey the same commutation relations as M. Okay? We'll then just put those matrices in the place of M. We'll get new objects here, and that'll be a new representation of the Lorentz group. So in finding a new representation of the group, the thing to do is to find a new representation of the algebra. And what that means is you find other matrices which obey the same commutation relation. Okay, so that's the goal now, is to do that. Yeah, please. Why do we? Oh, good. So you know, we want to consider fields. So some arbitrary field phi a, which consistently transforms. Okay, so there's always going to be this. This is phi a of x. There's always going to be this part here. But what we want is that perhaps there's some way that the internal indices of phi a can transform into each other in a consistent way under a Lorentz transformation. So a good example is if this is just a mu index, and that's telling you that there's a vector which rotates. So the question is are there any other ways that you can have fields where their indices sort of transform into each other in a consistent way? And consistent in this case means that these d's here satisfy basically the same product structure as the Lorentz group, which means this. And so we're trying to find matrices D which obey this, and in doing that, what we're going to do is find new matrices instead of M which obey this. Okay?
So if you find some matrices that obey this the algebra version, how do you know that? How do you know what spin it corresponds to the explanation?
Good. So the slightly pedestrian answer to that, there's probably more elegant answers, but let me tell you the pedestrian physical answer is the following. You have a new representation. You introduce a new field, so that, if you like, that's some column vector that this representation is going to act on. You then write down a Lagrangian described by that field, or obeyed by that field, if you like, a Lagrangian which captures the dynamics of that field. And then you go through the quantization procedure. You get the angular momentum operator, which is what you get by invariance under rotations. And you act with that angular momentum operator on a one-particle state, and a number pops out. That number is the spin of the particle.
Okay, so like the number, like a hat, it's just.
Yeah, it also is as well. So what happens is there's a classification of, for the Lorentz group, a classification of these representations. And the classification is in terms of spin 0, 1/2, 1, 3/2, and so on. So you know, what I'm saying is that there's only a certain finite number of, well, a class of matrices which can obey this, or really this. These matrices will, there'll be matrices of a certain size, and basically the size of the matrix is going to tell you the dimension of the representation, more or less. We'll see all this explicitly in a particular example over this lecture, so it might become clear. Other questions? Okay, so what we're going to do is find new matrices which obey representation which obey these commutation relations. And it's called the spinor representation of the Lorentz group. And to start with, I'm not going to attack this directly, but I'm going to define some new matrices, which are usually called gamma matrices and obey something called the Clifford algebra. Okay, so the Clifford algebra, I think Malcolm introduced this as well. Okay, have you seen these anti-commutator expressions before? Good, and this is the unit identity matrix. Yeah, it's supposed to be sort of a calligraphic one. Mm-hmm.
Why multiply by 1 already got an eta there?
So this is just stressing this eta is is either plus or minus 1 depending on this mu and nu index. But these are going to be matrices of a fixed type.
Okay.
And so this comes with matrices of a unit matrix of that size.
Because we're finding two indices.
Yeah, exactly. There'd be an alpha and a beta index here. Here, say, these would be multiplied together, and then the alpha and beta index would be here. So this is a matrix equation.
Yeah.
Yeah.
Sorry.
Yeah, it's a good. It's a good question. Okay, so this is for I equals 1, 2, 3. So what we want to do is find 4 matrices that have the following property, that if you square gamma 0, it gives you the unit matrix. If you square gamma 1, gamma 2, or gamma 3, it gives you minus the unit matrix. And that all of these matrices anti-commute with each other, meaning when you pass one through each other, you pick up a minus sign. Okay, so that's the definition of a Clifford algebra. Notice that I could define this in any dimension at all. The mu and the nu run from 0, 1, 2, 3 for us. But if I'm in some d-dimensional space, this also makes sense. It also makes sense if I'm in Euclidean signature or different signatures of space-time. And the representations of this equation are kind of interesting as you look in different dimensions of space-time. This is particularly important for supersymmetry and string theory, and there's some nice relationship to things like Hopf algebras and various nice mathematics. So this is basically a cute equation in mathematical physics. The solutions are well known, but there's some interesting properties in these solutions. So let me just tell you a set of matrices, of 4 matrices, which obey this equation. So the simplest representation is in terms of 4 by 4 matrices. Okay, what I mean by this is that you could start to look for 2 by 2 matrices which obey this. You won't find any. 3 by 3, you won't find any. If you look at 4 by 4 matrices, there's a set that obey this. The 4 by 4 matrices are written in 2 by 2 blocks. And these sigma I here are the Pauli matrices. Which should hopefully be familiar. Okay, you can check that these matrices obey these equations, and it's worth checking. Okay, now these aren't the only solution to these equations. And you can sort of see that trivially, because if I multiply each of these gammas by a U matrix here and a U inverse here, that's also guaranteed to solve the same equations. So there are many other representations. So if I take any invertible matrix U and multiply it on the left and these gammas on the left and right by U inverse, it still satisfies the Clifford algebra. However, there's a theorem that up to this equivalence, this is the unique, irreducible representation of the Clifford algebra. Okay. Irreducible here means that if you find a representation, you can't sort of split it up into diagonal blocks in such a way. So for example, there's an obvious 8 by 8 representation that basically has all these in the top left corner and then these again in the bottom right corner. That also obeys the Clifford algebra, but that's called reducible because it's basically constructed from this, so it's not interesting. So it's a theorem, but one that I'm not going to prove, that up to this equivalence, meaning multiplying by U and U inverse, there is a unique, irreducible representation of the Clifford algebra. And this particular example that we've got here, this particular choice, this has a name, and we'll learn why this is the name next week, but it's called the chiral representation. So this choice of gamma mu is called the chiral representation. Yeah.
So unique 4 by 4, so is there a unique irreducible representation for every like?
No. So this is really the statement that the 4 by 4 is the only irreducible representation up to this equivalence. So if you look for representations of higher dimensions, they'll always factor into sort of 4 by 4 diagonal blocks. So they'll always just be constructed trivially from these kind of representations.
Okay, so there's just no 5 by 5.
So there's no 5 by 5, no 6 by 6, no 7 by 7. There is an 8 by 8, but it's just made by 2 of these put together, and so on. Yeah. Questions? Okay, so I've just kind of pulled these gamma matrices out of the blue. What I now want to do is show you what these gamma matrices have to do with the Lorentz group. At the moment, they're just some random matrices that obey a nice equation. So let's see exactly what these have to do with the Lorentz group. So what does the Clifford algebra have to do with the Lorentz group? And the trick is to look at the following set of matrices. And there's 6 of these matrices. Okay? So remember, these gammas anti-commute to give 1, or 0. They anti-commute to give the eta rho sigma. But here we're going to commute them instead. So why are there 6 matrices here? There's 6 matrices because obviously if rho and sigma are equal to each other, this gives 0. And for example, the matrix that I call S01 is equal to minus the matrix that's S10. So it's this same issue that if you have 2 indices that run from 1 to 4, or 0 to 3 in this case, and you construct something that's anti-symmetric, there's 6 objects you can make from that. Yeah, exactly. So that's the point. This is guaranteed to be anti-symmetric in the by construction. It's equal to minus S sigma rho. Okay. This isn't anti-symmetry in the matrix indices. The matrix indices have all been left implicit here. You know, the rows and columns. So this is anti-symmetry in the label, which tells you which matrix you're looking at. Okay, we all good? So here we've got 6 matrices. And what I want to tell you is that these 6 matrices S have a very special property, and the property is the following. That if you commute 2 of the S's, they obey the following commutation relation. And something's wrong. There's a new here. Thanks. Thanks for the puzzled look.
Is there a nicer way of writing that in terms of permutation or something?
Not that I know of. And you could try playing around. It's something which, well, it's something which has to be anti-symmetric in rho and sigma and mu and nu. So I guess you could put, you could try and put square brackets around pairs of these, which, you know this notation, that sort of means people sometimes write this to mean, I think there's a factor of a half, x mu nu minus x nu mu. This is a notation that people sometimes introduce. But because you've got 2 pairs, it's not going to be clear which bracket's going around which. So I think this is the cleanest way to write it. Okay, what does this mean? This is exactly the same commutation relations that we found for the m's. Okay? What this means is that the s's provide a representation of the Lorentz Lie algebra. By which I mean that equation I wrote down at the beginning of the lecture, which was m commutator m equals m. OK, I could go through the proof of this on the board, but it should be clear what you need to do, and I'm going to leave it as an exercise. So we've got these S's defined in this way. You shouldn't use the explicit gamma matrices that I gave you to get the explicit S's. You could, of course, but this proof doesn't require you to do that. All it requires you to use is the property of the gamma matrices, meaning that they obey the Clifford algebra. They anti-commute to give 1 or 0, depending on the eta mu nu. Okay? So given this definition of the S's and the fact that gammas obey the Clifford algebra, you can prove that this is true. Okay? So I'll set that as an exercise. If you want, you can add it to the homework that you've been given. Again, it's one of these things you should really just do once, and then you'll be happy with. But it's a really important result. So do it when you like, but you should do it once. Okay, yeah, don't hand it in. Okay. Yeah, let me just tell you that there's not quite a trick, but an intermediate step that's worth proving. By the way, I can also tell you that this is all done explicitly in the notes. So every single step is done there. So the trick is to first prove, you see, this has 2 gammas and this has 2 gammas. So it's actually useful to first prove a slightly easier thing. What happens if an S commutes with a single gamma? Sorry, that's probably not very well. Let me just read this out if people can't see it. This is an S with a mu nu index commuting with a gamma with a rho index. And it's equal to gamma mu eta nu rho minus gamma nu eta rho mu. A lot of Greek, yeah, exactly. Okay, good. Okay, so is it clear what we've done? We started with the Lorentz group, and we tried to abstract what the essence of the Lorentz group was. And I told you that it was the commutation relations between the infinitesimal generators. So then we find a clever way to construct new matrices which obey the same commutation relations. And the clever way is to first introduce this Clifford algebra, and then move on from there. So again, this is also something which you can do in every single space-time dimension. Okay, so what does this mean? It means we're going to introduce a Dirac spinor. And this is a complex valued object. That I'm going to call psi. So it's a field now. Okay, it's a field over space, just like these scalar fields. And this alpha runs over 1, 2, 3, 4. Yeah.
Why over 1, 2, 3, 4 instead of the 0, 1, 2, 3 convention?
Oh, good. Let me write these equations on the board, then I'll come back. In some sense, it's just a choice.
Well, yeah. You made an argument in the notes about why, and I didn't quite.
Oh, so the answer is that this isn't the mu index. It's really important. So, you know, I could call them what I like, but if I called them 0, 1, 2, 3, that would lead you to suggest that the 0 component was something to do with time, and the 1, 2, 3 was something to do with space. And that's not the case. This definitely isn't the mu index. Okay. And I'll talk more about this. Okay. So, let's see. Somehow I've got this up in the notes. I mean, one aspect of this not being the mu index is it's actually not going to matter whether it's up or down. There's not going to be minus signs that come in. But let me just make a choice. So I think it's, what is it in the printed notes? It's up. Good. Yeah, let me stick with up then. OK, so the property of this field is that under a Lorentz transformation, this transforms in the following way, where lambda is some Lorentz transformation, which, as we've seen, can always be written as the exponentiation of these particular matrices M, which we saw in the last lecture. They're just particular matrices with 1s and 0s, and there's 6 of them. And then some 6 numbers which tell you which Lorentz transformation you're doing. This matrix S is another 4×4 matrix which you get by exponentiating the same numbers, but now multiplying the new generators instead of the old generators. These matrices S of lambda form a representation of the Lorentz group, which means that if you multiply 2 of these together, you basically get the same thing as multiplying 2 of these together, or more precisely, this equation holds. And this equation holds precisely because these S's obey the same commutation relations as these M's, which is what we've shown. Okay? So what we've done is construct a representation of the Lorentz group by finding matrices S which obey the same commutation relations as the M's.
Is S matrices the standard representation you see when you do this, or are they some weird representation?
What do you mean by standard?
There are representations you see with the, you have like gamma along the diagonal for the gamma and theta minus theta, and then the gamma is something like 1 plus. I don't know. I guess I've seen, like, if you do it for like a boost in one direction. Oh,
we're going to figure out what, you see, at the moment, what these S's are, these sort of representations of the group, depend on the representations of the algebra. And the representations of the algebra depend in turn on the representations you've chosen for the gamma matrices. So for that specific representation of gamma matrices that I called the chiral representation, that's the one I wrote on the board with Pauli matrices, we'll figure out what this is very shortly. And then we can just see if it's the one you're familiar with or not. It probably is, but I'm not quite sure. Yeah, please.
Algebra, and I believe there are smaller dimensional representations on the Lorentz group.
Absolutely.
They make physical sense.
Yeah, there are, and we'll get to them. Yeah. So we've constructed a representation of the Lorentz group. It turns out it's not quite that. Although the representation of the Clifford algebra was irreducible, this representation is not irreducible, meaning you can sort of split it into 2 smaller ones. And we will come to that maybe next week. Yeah, sort of, yes. Yeah, but there's a whole story to tell there that will take some time. It's not to do with things connected to the identity and things like that. It's not really that issue. But we'll get there. Yeah, please.
You choose psi to be 4.
Yeah.
They plug in gamma or matrix and 4×4 and so on. Is there, besides just wanting it to be irreducible, is there a reason?
Yeah, so I could say a few things about this. So firstly, this goes from 1 to 4. And as you pointed out, it goes from 1 to 4 because this is a 4 by 4 matrix, and this is a 4 by 4 matrix because this is a 4 by 4 matrix, and this was a 4 by 4 matrix because that Clifford algebra had a unique irreducible representation that was 4 by 4. So I could take the larger representations of the Clifford algebra, let me call them capital gamma, would basically be of this kind of form. So this is an example of a reducible representation. You'll plug through everything, and what you'll get here is a representation which is S lambda, S lambda. So it's really just like it's acting on two fields. And it's not rotating the indices between the two fields. It's just rotating the indices of one field and another field. So we can have things like this, but it's basically the same representation, but just saying you've got two fields instead of one under that representation. Okay. Is that the question? Okay. There's one other thing I want to stress, which is that I've insisted this thing is complex valued. So why is that? I could think, well, let me just write down a real vector here. Why does it have to be complex? Well, the reason is that if I wrote down a real vector here and I acted with a Lorentz transformation, these matrices S are typically complex. So I'd end up with something that was complex after a Lorentz transformation. The reason these matrices S are complex is because these guys are complex, and the reason these guys are complex is because the representations of the Clifford algebra are necessarily complex. Okay? There's a caveat to that whole story, which is called Majorana fermions. It's not completely unrelated to the issue you raised about smaller representations, and I may or may not talk about Majorana fermions next week. But there are certainly smaller representations of the Lorentz group that we will get to next week. Yeah. Sorry? That's a great question, and the honest answer is we don't know. Yeah. There's a very good reason why neutrinos might be best described in terms of Majorana fermions, but we're not sure. They also arise in beautiful ways in condensed matter systems. So rather esoteric condensed matter systems, but actually some of the most interesting ones. So there's something called a fractional quantum Hall fluid at 5/2 filling, which has particles which are neither bosons nor fermions, nor something in between, but obey something weird called non-abelian statistics. And they're best described by Majorana fermions. There's also something called P-wave superconductors. So they appear in strange settings. But in standard model, we don't know is the right answer. Please.
Normally, when you have these spinors that go from 1 to 2, like model optimistic, then if you can think of the polymatrix as switching a spinor index to space-time index.
Yeah.
Go from 1 to 4.
Yeah, this is not unrelated to the question earlier about having smaller representations, and we'll just get there. It will probably be the next lecture, not this one. But we'll sort of make this a bit more explicit and get there in time. Are there any other questions that I can postpone till next week? Okay. So you might be worried about something. We started with a particular non-trivial representation of the Lorentz group, which is sort of the defining representation. It's this set of 4x4 matrices, and we know what it acts on. It acts on vectors that have this index mu that goes from 0 to 3. And now I've told you, well, we've got a new representation, and it also acts on objects with an index that has 4 entries. It goes from 1 to 4 now instead of 0 to 3. But as you asked, how do I know it goes from 1 to 4 and not 0 to 3? Or maybe another way to ask this question is, how do I know that I've not just wasted half an hour of my life and actually constructed a representation in a weird way that turns out to be exactly the same as this guy? Yeah, they're necessarily the same thing, absolutely. So this is telling you I'm going to rotate by 90 degrees around the z-axis. That's what's happening in space. What happens to the indices here should mimic the fact that you're doing that rotation. So these are the same set of numbers for a given Lorentz transformation. Yeah, it's just these generators which change.
Why don't you have the S representation on the argument inside the Q?
Oh, because we know what this guy is. This is an object with a mu, not an alpha. So you know, this is we have space. That's kind of where we started, and we're doing a Lorentz transformation on space. So that's just not up for grabs. That's almost the definition of the Lorentz transformation. What's up for grabs is the fact that we've got a field living on the space, and that field has some internal indices, and it's a question about how those internal indices are rotating amongst themselves, like a vector in this direction rotating to a vector in this direction. So it's that thing that we can play with. Okay, this was sort of almost the defining feature of the Lorentz transformation. Other questions? Okay, so now I want to convince you that that this is actually different from this, that we haven't just gone through, you know, all these loops to end up with the same thing. That what we've got here is definitely something which is not the same as what we started with, even though they both happen to be 4x4 matrices. Okay, so let's look at the explicit S of lambda in the chiral representation. Okay, so the chiral representation means I pick those gamma matrices I wrote on the board, I figure out what these S's are by commuting them, and then I'm going to exponentiate these to get this. So this hopefully will answer the question you just had. So let's look at rotations. And so Sij, so for rotations, these indices here go over 1, 2, 3. That's because it was the Mij's here which gave me rotations. And this is equal to a quarter gamma I, gamma j. And if you just plug in those, if you plug in the chiral representation for gamma I and gamma j, that has Pauli matrices in there, what you get is the following. Okay, so this is what the generators of rotations are in the spinor representation. Now we want to introduce some numbers which tell us how much of a rotation we're going to do. These are the numbers that say, you know, rotate by 15 degrees and so on. Because there's an epsilon there, it's going to be useful to define these numbers also with an epsilon.
S00 does have something to do with time, but the alpha and beta indices on S are not.
Yeah, so this S rho sigma, alpha beta, these were constructed to match these. So these are the usual Lorentz indices going over 0, 1, 2, 3, but with this anti-symmetry, so they're really a label captures 6. These guys go from 1 to 4 and are not the mu index. Okay, so this is actually quite a nice notation because you see S12 was actually a rotation around the z-axis. And so omega 12 was how much you're rotating around the z-axis. And with this notation, it's actually, in LaTeX, this is called var phi. I'm going to call it var phi. This object here, var phi, with a 3 up there, that tells you how much you're rotating around the z-axis. So that's good. The var phi with the label k tells you how much you're rotating around the k-axis. So now we just plug it into this formula, and what we get is plus I over 2 is the following matrix. Okay. So what is this telling us? We have a 4-component Dirac spinor. This is telling us if we rotate by an angle var phi, this is how you act on that particular spinor. Okay. Is this clear? No? Yeah? Now there's something pretty surprising about this result. And what's surprising is the following. So consider a rotation by 2 pi around the z-axis.
They both have the same sign?
They both have the same sign, yeah. Actually, is that right? Do they have the same sign in the notes? It's a bit of a squiggle here. They have the same sign in the notes? And then they have the same sign in real life as well. Is there a question? Yeah.
The gamma IG runs gammas where I and J runs from 1 to 3 instead of 1 to 4. Because if you go back by the definition of this big gamma of
It takes 0 to 3, and if one of the components is a 0, that's telling you that there's a boost. And if both the components are spatial, 1, 2, 3, that's telling you it's a rotation. So at the moment, we'll just do rotations, and in a minute, we'll look at things of the form 0i, which are going to be boosts. Yeah?
Does that correspond with the interval because it's exponentiating the diagonal matrix, or is that?
The epsilons just cancelled. There were 2 epsilon ijk's.
Right.
But yeah, the fact you can do this easily is because it was diagonal, and so yeah, that was handy in this. Otherwise, it can be a bit tricky. But. Yeah, sorry, you're right. It's block diagonal, and so there's some trickiness for say the gamma 1 and gamma 2 pieces, but I've just hidden it in the notations.
No.
Yeah, thanks. Okay, so what happens if I take this and plug it in here? For this particular rotation, this matrix is not the unit matrix. It's minus the unit matrix. Which means that under a 2 pi rotation, this spinor goes to minus itself. Okay, so that's definitely not what happens for a vector. Right? You take a vector, you rotate it by 2 pi, you get back exactly the same vector. So this is the most striking difference between the spinor, between the usual Lorentz representation, the vector representation, and the spinor representation. Rotate things by 2 pi, they don't come back to themselves, they come back to minus itself.
How do we know you have the specification phi is really
Yeah, it's a great question. So what you should do, and I do go through this in the notes, is you should do this same thing for this. Okay, so for the actual representation, you should plug in the same value of var phi defined in the same way with the epsilon symbol, and you'll see that that this gives 1 and not minus 1. Yeah, so it's definitely worth checking that. It turns out it's actually this factor of a half here which is giving this this minus sign. But yeah, there's enough factors of a half floating around that you should be careful and check this. Okay, so you may have heard this statement before, that if you take spin half particles and you rotate them by 2 pi, they come back to minus itself. It's sort of tied up with Fermi-Dirac statistics for spin half particles. And that's always a little bit puzzling. And typically people say, well, it's got something to do with the quantum world and it's all puzzling. And I don't think that's really true. I think these are objects that can exist in the classical world. There's nothing quantum here. There's no operators. All we're doing is looking at representations of the Lorentz group and finding that there are new objects, new field objects, which have this property where when you rotate by 2 pi, they come back to minus itself. So it's a property of the Lorentz group, not a property of turning on H bar.
So it definitely seems like when you rotate most classical objects around by 2 pi, you don't get any sign. So like, why is this?
It does seem like that. And since you ask, I'll give you an example of a classical object. Can I borrow your folder? Okay. This object, we can rotate by 2 pi, and it comes back, well, it requires us to rotate by 4 pi to get back to itself. Okay? So this is the rotation by 2 pi. Okay? Okay. I'm not back where I started from, and I probably should have chosen a lighter object to demonstrate this with. If I rotate by another 2 pi, okay, let me just prove to you I'm not cheating. This is coming back to where I started. This is 2 pi. If I rotate by another 2 pi, I get back to where I started. Okay? So there are classical objects, you own one of them, which you need to rotate by 4 pi to get back to where you started. Now, it's a little bit of a swindle, obviously, but it's actually not totally unrelated to this representation of the Lorentz group. So what's going on here is that I was rotating, but subject to certain boundary conditions of infinity. The boundary conditions, and infinity being my shoulder in this case. Okay? And yeah, like I said, it's not totally unrelated to the existence of this representation. But it's a bit of a swindle, obviously. It wasn't a field I was rotating and so on. So there are examples. Yeah?
What would you have done differently to get this
Good. I'd have to look for a different representation. Yeah. So this whole procedure has been to build a given representation of the Lorentz group. And the representation has been classified. Actually, representations of the Poincare group of what you should really study. That includes Lorentz plus translations. They were classified by Wigner. And there's lots of interesting stories that can be told. In particular, nothing bigger than spin 2 is useful in a quantum theory in some sense. So there's lots of beautiful results about this. Questions? No? Okay, let me tell you about boosts. For boosts, we're interested in S0I. These are what the generators look like. They're just Pauli matrices. I'll write the boost parameter in terms of chi, and then compute the boosts. Plus a half chi dot sigma. Okay. Yeah, thanks. Yeah. Right. Okay, this is what I get for the boosts. Now there is a minus sign difference, but there's no factor of I here. That's important. It's just a half, not an I over 2. Sorry. I could probably return to your question now. You said, are these the familiar S matrices? So this is what they are. They're exponentiations of the Pauli matrices with no I's or I's, depending if it's boosts or rotation. So is that what you were expecting? Or?
My question was, are these the same as the representations acting on space-time?
Oh, good, good. So that's definitely a no. Yeah, yeah. So let me just stress, because this is going to be very important in what follows. When we computed the rotation matrices, there was an I that sat here. That means when we compute the Hermitian conjugate, it comes with a minus I, and in particular that means that S dagger is the inverse of S. Okay, so S dagger times S is 1. That means that for rotations, these representations are unitary. But for boosts, there's no I, and so for boosts, this is not true. Okay, this is actually a general statement. There are no finite dimensional unitary representations of the Lorentz group. Okay? And here we're seeing an explicit example in this case. So in fact, there are no finite dimensional unitary representations of the Lorentz group.
I have that.
Uh-huh.
Are there infinite dimensions?
Yeah.
Okay. The other question is, why doesn't the lack of unitarity bother us?
We're going to have to deal with it now. Yeah. Other questions? Yeah.
So I guess effectively everybody, why does the lack of unitary take out of this? I mean, if I understand correctly, we're only looking at how the, how the field kind of is transformed.
Yeah. No, so it bothers us when we come to construct an action which should be invariant under the Lorentz transformation, which is exactly what we'll see now. Hold on, and then we'll see exactly where this is going to raise its head. Any other questions? No? Okay. So, what we have is this, this lovely new field, Dirac spinor, transforms in an interesting way under Lorentz transformations. So what we would like to do is understand what kind of equations of motion this could obey. And in particular, what kind of equations of motion it could obey that are invariant under Lorentz transformations. Probably I should say covariant under Lorentz transformations. But in particular, the requirement I want is that if I have one solution of the equations of motion and I act on it with a Lorentz transformation, it's still a solution. Okay. So how can we figure out an equation of motion which is invariant, covariant, under Lorentz transformations? Well, the trick is to write down an action, or a Lagrangian, which is invariant under Lorentz transformations. Okay, we've been doing this all of last week. So what we want to do now is try and write down an action for psi such that it's invariant under Lorentz transformations. Okay? So we want to write an action that's invariant under Lorentz transformations. But, you know, we've got this spinor index floating around, and so obviously we're going to have to write down an action where you manage to contract spinor indices together to get something that's invariant. And so what's the obvious thing to contract psi with? Well, the obvious thing, we want an action that's real, so just take psi dagger, okay, and then contract the indices. So define psi dagger of x, by which I mean you take the complex conjugate and then you take the transpose. So just think of psi as a vector, and it's the obvious thing. You know, you flip it up like this and you take the complex conjugate. So under a Lorentz transformation, psi of x goes to this, and psi dagger of x goes to this. Okay? This is now just the conjugate of the one above. But now you can see that there's kind of a problem. And the problem is that this representation is not unitary. And in particular, that means that if I contract this psi dagger with this psi to get a scalar by contracting these indices, this is not going to be a Lorentz scalar. Okay, you see the problem. To be a Lorentz scalar, you would want this S dagger to cancel this S and give you 1. But it's not a unitary representation, so that doesn't happen. Okay? This should answer your question. Why do we care about unitary representations? It's causing us a bit of a headache here because we can't get a Lorentz scalar just by contracting this and this. So we're going to have to work a little harder. Okay, so let's just try and understand a little better why this is not going to be a unitary representation. Yeah?
So we defined psi dagger and psi.
Yeah, it was on this board just here. It's the obvious thing. Do that in complex conjugate.
So do we actually need this to be in the action? Did we just decide that we wanted an action?
So what I want is an action which has several properties. It's got to be real. And I want it to be a Lorentz invariant action, which means I want it constructed out of Lorentz scalars. So the game we're playing now is how can I construct a Lorentz scalar out of psi?
The only way to make it real is to have psi and psi dagger.
Yeah, it's clear you need something like that, right? And we're gonna do it in the end, so maybe it's just worth holding off and seeing how it works. But the naive thing that you would do with a complex vector doesn't work. Okay, so let's just look a little closer about why this was not a Lorentz, a unitary representation. So recall that S was the exponentiation of the generators. So if we wanted S to be unitary, so if this guy was going to be unitary, we'd want that this guy was anti-Hermitian, meaning that when we took the dagger, we get a minus sign. Okay? If that were true, and it's not true, but if it were, it would mean the dagger of this, you just put a minus sign there, and then that's the inverse, which is the definition of a unitary. Okay, so this is what we would want if this were to be unitary. But just working backwards, S is defined in terms of the commutators of the gamma matrices. So this is the Hermitian conjugate of the generators. And if we wanted this to be true, we've got a minus sign here already, so we'd either need all the gammas to be Hermitian or all the gammas to be anti-Hermitian. Okay, if we could arrange that, then this would be true. If okay, you guys following? So if either of these were true, this equation here implies that this is true, and then that would mean that the representation was unitary. So let's just now see why this can't possibly be true. And it's very easy. It's that if you take gamma 0 squared, that gives you 1, which means that gamma 0 has real eigenvalues and can be Hermitian. But if you take any of the other guys and square it, you get minus 1, which means that they have imaginary eigenvalues. Which means that you can always make them anti-Hermitian, but never Hermitian. Okay, so the goal of this exercise is just to understand why the Lorentz group wasn't unitary, and we can trace it back to the signature of spacetime. It's the fact that the gamma 0 square to 1, the gamma I square to minus 1, that means that the gamma 0s definitely have real eigenvalues, but the gamma i's have imaginary eigenvalues. And that means that you can't make, the gamma 0 you can make Hermitian, but never anti-Hermitian, and the opposites for gamma i's. But we need all of them to be the same if this was to be a unitary representation. Okay, so the reason this wasn't unitary is because of the minus sign in the Minkowski metric. Is this clear? People following? Mm-hmm. Absolutely, yeah, and because it's it's a compact Lie group, the Euclidean. No, it's the rotation. Oh, okay. The rotation group, right? The Lorentz group we're comparing to the rotation group. Yeah. Yeah. However, this also sort of tells us how we get out of this problem. So if gamma 0 is Hermitian, and gamma I is anti-Hermitian, it means that if we take any gamma matrix and multiply it on the left and right by gamma 0, we get the Hermitian conjugate of that gamma matrix. The reason is that if this is gamma 0, it's just gamma 0, but if this is gamma I, you commute this round here, you get a minus sign, and then you get minus gamma I. If you follow all this through your definitions, what you find is that when you take the Hermitian conjugate of a Lorentz transformation, you don't quite get the inverse, but you get the inverse Lorentz transformation with gamma 0s multiplying on either side. I realize I'm going a bit fast here, but it's fairly straightforward, so you'll probably just have to read it afterwards. Bruno.
Just like to know whether when you write if gamma 0 dagger equals gamma 0 and I dagger,
Yeah.
is it only in the case of this particular 4x4 the full-dimensional representation, or
Yeah.
any full-dimensional representation it will still be?
So that chiral representation that I wrote down has this property. Now, I said in general, I can act on that chiral representation with any invertible matrix, u to the minus 1. If I choose any arbitrary u, it won't have this property. So what we'll do from now on is pick representations like the chiral representations for which this holds. Okay, so the purpose of this was to try and get ourselves around this problem. We couldn't form a Lorentz scalar of psi dagger, psi, because the Hermitian conjugate of S wasn't the inverse of S. But now we see that actually it's the inverse of S with gamma zeros multiplying on both sides. So with this in mind, what we do is we introduce the Dirac conjugate. Okay, so it's going to be denoted with a bar instead of a dagger, and it's the same as the dagger, but you multiply by gamma 0. Okay. So now I want to tell you how you can start to construct Lorentz scalars. Okay. So the first claim is that if I take psi bar psi instead of psi dagger psi, that's a Lorentz scalar, by which I mean that when I do a Lorentz transformation, the only thing that happens is the argument x changes. None of the spinor indices get screwed up. Okay. What's going on here? Well, there are s daggers and s's here, but now once you start passing them through gamma zeros, the s daggers actually turn into s to the minus 1s and kill the s from there and do what you want. Okay, so again, it's just worth checking that that's true. The details are in the notes, but it's not hard to see. Slightly trickier to see, but it's also in the notes, is that this is a Lorentz vector. So what do I mean by this? I mean that this object here transforms in the same way as a vector field under the Lorentz transformation. Okay, this is a bit trickier to see. What's going to happen is you're going to get an S dagger here and an S here. The S dagger, you're going to have to move through the gamma zeros, become S to the minus 1, but then you have to pass it through the gamma mu. So what you get is basically commutations of an S with a gamma. But I did write down the expression earlier for what that is. It was the intermediate step that you need to first prove before you prove that the S's satisfy this Lie algebra. So once you use that, this lambda turns up, which is the original representation, not the not the spinor representation, and the whole thing transforms as a vector. Okay. Okay, so both of these I'll leave as exercises. You can do them over the weekend, or maybe we'll do them next week in a tutorial. You know, they're all kind of tedious exercises because it's just multiplying matrices and commuting things past each other. But again, they're things you should do once just to convince yourself that this is true. Yeah? No, again, all of these exercises just require you to use the fact that gammas obey the Clifford algebra. Yeah, so the chiral rep would work. Actually, it's not true. They obey the Clifford algebra, but you also need that you've chosen a representation that obeys this. So not necessarily the chiral representation, but one that obeys this. Yeah, where the U and the U inverse are U and U dagger, basically, where you multiply by U.
So are we ever going to relax that condition?
No. So yeah. At least I don't know of any examples where people work in bases that don't obey this.
So when you actually find the Dirac equation, are you just going to have?
We're going to be working in, yeah, typically when people write down Dirac equations, they often don't specify which representation of gamma they're working in, but this is always implicit. Yeah. And sometimes if they're doing explicit calculations, they'll give the representation as well. Okay, so we've got some Lorentz scalars, and we've got a Lorentz vector. So, yeah. I'm going to answer this question after the lecture because we're already 5 minutes over, and I just want to get to the punchline. So the Dirac equation. We want to write down a Lagrangian, which is a Lorentz scalar. And we've now constructed a Lorentz scalar, psi bar psi, and a Lorentz vector, which is with a gamma stuck in the middle there, that we can play with. So from this, it should be clear that the following action is invariant under Lorentz transformations. Is a psi bar okay, so why is this true? This is what we've just proven. The psi bar psi is a Lorentz scalar. We're integrating it against 4x, d4x, and now we've got something that's actually invariant, the action. The psi bar gamma psi is a Lorentz vector, so to get something that's Lorentz invariant, we need to contract it with another Lorentz vector. But we've got one floating around, the derivative operator. Okay? So those two claims I wrote on the board imply that this is a Lorentz invariant action. Now the equation of motion well, we've seen these things before. Psi is complex. So to get the equations of motion, it's useful to think of psi and psi dagger as independent and vary with respect to one or the other. Now, in this case, varying with respect to psi dagger is particularly simple because there's no derivative acting on psi dagger. So varying with respect to psi dagger basically just means crossing this off. So the equation of motion is this. By the way, I should stress, this is a 4x4 matrix. This M now comes with an implicit unit 4x4 matrix. And this is now a 4-component complex column vector. Okay. So this is the Dirac equation, which I think you saw in Malcolm's course. So a few things to say about this. Actually, an infinity of things to say about this. This is completely gorgeous. I think it's almost certain that this is the most beautifully amazing equation ever written down in the history of human civilization. You know, what it did for physics was incredible. Dirac immediately predicted that the magnetic moment of the electron was 2. I think Malcolm walked you through that calculation. A couple of years later, he figured out that this equation predicts antimatter, which is you know, one of the great all-time achievements. This equation is still an integral part of the Standard Model. All the fermions that we have, quarks, the leptons, the electrons, the tau, the muons, the neutrinos, they're all described by this equation or variants of this equation. So it's really a key part of the Standard Model of particle physics. In the hands of mathematicians in the 1960s, they revolutionized areas of mathematics. People like Atiyah and Singer developed index theorems by figuring out what this equation could be used for in mathematics. So you know, this is about as good as it gets in terms of theoretical physics. One of the surprising facts about it is that it exists at all. What Dirac managed to do was write down an equation which is linear in derivatives, but nonetheless is Lorentz invariant. Okay? Now we've just proven this on the board, and it took us a while to do. And the key is the properties of this gamma here. Okay? To sort of show you how amazing this is, suppose we tried to do this for a scalar field. So there was no index structure here. It was just some scalar field. And we wanted to write down an equation linear in derivatives. Well, you'd have a mu index floating around, and you'd have to write something here which also had a mu index. But you know, there's nothing natural that has a mu index. If you write down a vector, a 4 vector with a mu index, that points somewhere. You know, you'd have to choose to point to my mother's house or somewhere in the universe. And what you'd end up with is an equation which certainly wasn't Lorentz invariant. You know, it would depend on where my mum lived. So what we have here is somehow the fact that there are these natural vectors floating around in the universe that are given to us. What's interesting about them is it's a vector of matrices. And the whole point about this equation is that these gamma matrices rotate naturally like a vector under Lorentz transformations. So in some mathematical sense, that was Dirac's great discovery, that there are these new objects in the universe, these rather abstract gamma matrices which rotate as a natural vector.
So it seems intuitively obvious that we can't actually have natural vectors, even natural matrix value vectors, floating around in the universe, otherwise we'd be able to measure them. So
it seems intuitively obvious, and it's wrong, because we've just demonstrated that this object here, psi bar gamma mu psi, is a natural vector-valued object in the universe.
So then how do you measure? Like, it seems like we should have, is there any sort of invariant, like, gauge of this equation?
Nope, no gauge invariance. This is it. Okay, other questions? So you know, it's not that this doesn't have consequences. It has untold consequences, and most of theoretical physics is built on the consequences of this, in the sense that fermions exist, and you know, that leads to all of condensed matter physics, and that leads to all of biology, and so on. So you know, it's important. But you know, you should also be aware that these gammas are a little bit abstract. It's theoretical physics. What can I tell you? Other questions? Tibra.
You have already mentioned this, that psi is also a solution to the Fine-Gordon equation.
Yeah, we'll get to that in the next lecture. But I think Malcolm said it already. But yeah, but it's almost like a check. The reason this is Lorentz invariant is not because psi is a solution to the Sine-Gordon equation. The reason this is Lorentz invariant is because of the astonishing properties of these gammas. Leo.
I don't expect an answer, but let me phrase a question. Does the same kind of structure exist 2, 3, 10, 11, or 26 dimensions?
Absolutely, and every single one of those dimensions you mentioned, apart from 11, is special in terms of what gammas you can have. So the gammas solve these equations here. And you can take the mu and nu index to run over any dimension you like. In 2, 3, 4, and 10, interesting things happen for this equation. The solutions have interesting properties to do with the fact that the Lorentz, it's also true here that this is not a reducible representation of the Lorentz group, and we'll come to that later. So the fact you pick 10 and 11 is probably because string theorists talk about 10 and 11, and the reason string theory managed is to exist in 10, and in actually the 26 has little to do with, has something to do with spinors, but it's not as direct. But the reason that the 10 exists for superstring theory is really, in large part, to do with properties of this equation in 10 dimensions. Yeah?
You said this equation has forms in 2 and 3 dimensions, but earlier you said that the gamma matrices have to be these 4 by 4 matrices.
Yeah, so they have to be 4 by 4 if we're in 3 plus 1 dimensions. Or, let me say this explicitly. If mu goes from 0 to d minus 1, so d is 4 for our world, the dimension of the gamma matrix, the dimension of the gamma matrices is 2 to the integer part of d over 2. So you want to solve this equation here, you have to find the irreducible representation has dimension 2 to the d over 2. So for us, that's 2 to the 2, which is 4. If you go up to 5 dimensions, it's still 4, but if you go up to 6 dimensions, you need 8 by 8 matrices. In 7, it's still 8 by 8. By the time you go up to 8 dimensions, it's 16 by 16, and so on. Other questions? It's definitely time for coffee.